Okay, another dotted line on the map. There are lots of dotted lines in astronomy, but this is one of the most important ones, the ecliptic. I've been avoiding mentioning it during the first half because we've been mainly concentrating on the celestial equator and how that moves around in the sky when we change our position on the Earth, or how its angle with respect to the horizon changes with our latitude and so on. But the ecliptic, if you get down to it, is actually more important. That's the plane of the Earth's orbit projected onto the celestial sphere. How's that different from the celestial equator? That's the Earth's equator onto the celestial sphere. And the 12 constellations that are along the ecliptic, if you look on any sky map, you'll recognize those as the well-known constellations of the zodiac that astrologers like to use and make something of. So the constellations along the ecliptic are the zodiac constellations. Now, since all of the other planets in the solar system, except for a few Plutophiles out there, you would agree that all of the planets of the solar system now are in the same plane as the Earth's orbit around the sun. And so is the moon within a few degrees. So what does that mean? That all of the objects in the solar system are going to be somewhere in the sky along the ecliptic or very close to it. You'll never find Venus in the Big Dipper, for example. It will always be in one of the constellations of the zodiac, one of the 12 along the ecliptic. And that's true of the moon or the sun by definition, or any of the other solar system objects are all along the ecliptic. As the Earth goes around the sun appears to move eastward around the sky during the course of the year about 1 degree per day. Since there are 365 days in a year and 360 degrees in a circle, that works out within a close approximation of 1 degree per day going towards the east. The moon and all other planets are in the same plane, so all of them will be found close to the ecliptic in the background of the constellations of the zodiac. By the background, I mean that even though these constellations are made up of nearby stars in the Milky Way, 1,000 light years or less away, we're only talking about miles to the planets. So they're in the foreground, and these constellations are definitely in the background as far as the scale is concerned. Unless you all just went close to a magnetic field during the break, I don't have to go over all this again. This is in case it's 2 different months that we do it. And the celestial equator, it's all about the celestial equator.
Yeah, but just a general question.
Yeah.
How long did it take really astronomers to figure out all these relationships that you've been talking about tonight?
Not as long as you would think, and not as recently as you might think. When we get to the early history of astronomy, which I think is now in August, we'll see that most of this was done by Hipparchus, BC. There's an amazing amount of stuff that was done, because this doesn't take spectroscopy to do anything that I'm talking about tonight. And they didn't have to understand anything. All they had to do was record the motions and catalog things. Later on, the science caught up to it, and we have a lot more understanding of it now. But most of what I'm presenting tonight has been known for thousands of years. So it's a good point, but this is not new. Also, while I'm at it, I might mention this is the hardest one of the short course presentations to give. It is intricate and it's hard to use the software, but besides that, the subject matter itself isn't flashy. We used to do this one first because this is where it really starts, and nobody ever came back. So, that's why we put the introductory program in last month that shows what it's really going to be like. And this is like, whoops, time out to learn the alphabet and things like that we really need to know, but it gets way more interesting and spectacular and beautiful as we proceed. Although there are a few moments tonight where I think you appreciate learning some things that you might have wondered about before. It's more of a visceral experience later on instead of just purely intellectual. Okay, Earth's equator, okay, we've already done that. All right. That was the review of all of that. I hope none of that's brand new. Okay, here's the new thing. Most grade school kids can tell you that the seasons occur because the Earth's axis is tilted, right? Everybody knows that. If you ask them tilted with respect to what, then I don't know. So that's where you have to get a little bit more specific. If the plane of the Earth's orbit, the ecliptic, is defined as a flat surface like the table, and the Earth is a globe sitting on it like you would have in a classroom, it's got a tilt to it. The North Pole isn't straight up and down, is it? It's tilted. So that tilt is with respect to straight up and down in the plane of the Earth's orbit around the sun. So we've got the two planes, and the plane of the ecliptic is tilted with respect to the plane of the equator by 23.5 degrees. So the Earth's axis is not straight up and down, but is tilted over with respect to the plane of its orbit around the sun. We'll have a slide later on that's better than this, but a couple of slides down the road. So the celestial equator is then inclined to the ecliptic by 23.5 degrees. If the Earth's pole were straight up and down, then the ecliptic, its path around the sun, and the equator, the Earth's equator, would be the same in the sky. But they're not. They're tilted 23.5 degrees with respect to each other. So they intersect at 2 points. Like any two circles that are not in the same plane, they have 2 points of intersection where they have a point in common. And those points are referred to as the equinoxes, for the reason we'll see in just a moment. And they're the two separations where they don't intersect, the widest points apart from each other, are 23.5 degrees on the celestial sphere. And at those points, we refer to those as the solstices. And we'll see the reason for that very shortly. The vernal equinox is one of those intersection points where the sun, which is on the ecliptic by definition, that's the path of the sun around the sky during the year, is the ecliptic. I said it was the plane of the Earth's orbit, but that is a new thing. The fact that the Earth goes around the sun and it makes it look like the sun is going around the Earth, that is relatively new, like 400 years or so. So that's at the point where the sun crosses the celestial equator going towards the north. That's the beginning of spring. Whoops. That's the vernal equinox. The equinox is when the days and nights are equal, and vernal means pertaining to spring. So that's the beginning of spring in the northern hemisphere. And that is in the constellation Pisces. If you turn your planisphere so that the constellation Pisces is above the horizon, you'll see that the celestial equator, in fact, does cross the ecliptic at that point, and that's where the sun would be on the vernal equinox. We saw it going by in the planetarium software a little earlier, and the sun was now in Pisces. There's another equinox on your April sky map, if you're looking at that. There's another intersection point in Virgo, and that's the autumnal equinox, where the sun crosses the ecliptic heading south into the autumn. And that's referred to there. And that is on your April sky map. And it's in the constellation Virgo. Okay, when the sun is at an equinox, it's on the celestial equator. It's always on the ecliptic, right? That's by definition. But when it crosses the celestial equator, it behaves like any other star on the celestial equator. It's up 12 hours, down 12 hours. I think I made that point about 37 times in the first half, that anything on the celestial equator is up 12 hours and down. And that applies to the sun too. So on the first day of spring and the first day of fall, when the sun is on the equator, the days and nights are both 12 hours long. That's where the term equinox comes in, the equal night. So days, they're all over the world. Doesn't make any difference where you are. You have a 12-hour day and a 12-hour night on those 2 days of the year. Now the solstices are the opposite case, where the ecliptic is at the maximum distance, 23.5 degrees from the celestial equator. The north-south position stays the same for several days. It's actually following like a sine wave. If you think of the celestial equator as a straight line and the ecliptic, the path of the sun, it's actually a sine wave. And up at the peak of it and at the bottom of it, it's not flat, but it doesn't change much in up and down motion over a period of several days. And that's where the term solstice comes from, the sun standing still. It doesn't go any farther north. It hasn't started going back south yet. It's about the same distance from the equator for several days, and that's the origin of the term solstice. The summer solstice is in the constellation Gemini, and that is on your April star map. You find the constellation Gemini if you look near Castor's Foot, in fact, just about where M35, the open cluster in Gemini, is located. You'll see the celestial equator and the ecliptic are as far apart as they get on the map. Anywhere else, they're closer together. That's the 23.5 degree separation that you see there. And that's where the sun is on the first day of summer, the longest day of the year. At that point, the sun is as far north as the equator as it gets, which means it's up longer than it's down by the greatest margin. Another way to look at it is it's trying to get circumpolar. If it got a lot farther north, it'd be up all the time. But from our latitude, and we'll see how that looks at different latitudes, from where we are, that's as far north as the sun gets, so it's up more than it's down by the greatest amount during the year. Okay, so that's already there. The longest day marks the beginning of summer, usually about the 21st or 22nd of June. The winter solstice is in Sagittarius, which is not on your April sky map. It'll be one later in the year, but you can use the planisphere and turn to Sagittarius, and you can see there the ecliptic is as far south of the equator as it ever gets. And that's 23.5 degrees there. That's the winter solstice. So for several days, right ahead of Christmas, the sun is as far south as it gets. The days are as short as possible compared to the nights. And then after that, the days start getting longer once again. So the shortest day marks the beginning of winter. A couple of terms here, might as well get them over with. Declination is the equivalent of latitude. On the Earth, we measure how far north or south of the equator we are in degrees of latitude. Here we're 35 degrees latitude north of the equator. In the sky, declination is exactly the same thing. How many degrees north or south of the celestial equator you are, and we use and they're parallel to the equator, those lines that go all the way around the sky. And they're analogous to lines of latitude on the Earth. Abbreviated either DEC or with a lowercase Greek letter delta, measured north of the celestial equator with a positive number, or south with a negative number. That's a little bit different from latitude, isn't it? On the Earth, we say 35 degrees north or 35 south. In the sky, it would be plus 35 declination or minus 35. But if you just said north or south, everybody knows what you mean anyway, and it's not really wrong. That's just the standard way of doing it. Degrees are subdivided into minutes and seconds. You're familiar with that concept, the factor of 60. 60 minutes is 1 degree, and 60 seconds is 1 minute. So a minute of arc on the sky is 36/100th of a degree, 60th of a 60th. Right ascension corresponds to longitude on the Earth. Longitude on the Earth is the lines that run from the North Pole across the equator down to the South Pole. And if you drew all the longitude lines in, the Earth would look sort of like the sections of an orange. Think of those as the lines of longitude on the Earth or right ascension in the sky. And as with the Earth, where we start is arbitrary. Now, with the declination or the latitude, the equator is an obvious place on the Earth, right, between the poles. And there's no doubt that that's the 0 point either side. Same with the sky. But the longitude lines on the Earth are set up arbitrarily. You could make any one of them 0 and start counting from there, couldn't you? Well, where is the 0 longitude line? Well, it's Greenwich, England. The prime meridian runs through there. The French didn't much like that and had their own set of longitude running through Paris until actually not all that long ago, because they refused to adapt to the British system with the Greenwich as being the prime meridian. In the sky, it's again, we can pick any line of right ascension as being the 0 or starting point. But one that makes the most sense is where the vernal equinox is, where the celestial equator and the ecliptic cross in Pisces. If we call that 0 line, then they're numbered consecutively through 24 all the way around the sky, going eastward, just like you would expect. So right ascension, or alpha, runs from pole to pole in the sky, perpendicular to the celestial equator, just like longitude lines on the Earth. The 0 hour line intersects the equator and the ecliptic at the vernal equinox in Pisces, which I had you look at a little while ago. The 6 hour line, a fourth of the way around, 3 constellations over. From Pisces, what do we have? Aries, Taurus, Gemini. So that's a fourth of the way around, 6 hours. Then 3 more constellations, another 6 hours. After Gemini, then Cancer, Leo, Virgo. And that takes us back to the 12 hours, which is the autumnal equinox, directly opposite the vernal equinox. And back again, another 6 hours. We go through the winter solstice in Sagittarius is at 18 hours. Now, this doesn't come up an awful lot in amateur astronomy, but it will often enough to where you need to pick out a particular sky map. You look up the coordinates of a comet that's in Sky and Telescope. You need to know about where to look in the sky. If you have a whole book of sky maps, there's a lot of more places where that comet isn't than where it is. And it helps to get on the right map, and knowing how the relationship of right ascension and declination are will stand you in good stead. I picked the November sky map because on this one, the vernal equinox in Pisces is right there on the meridian. And we can see how we go over here 21 hours. Okay, going eastward, we go 3 hours, 6 hours, 9, 12, 15, 18, and on back around. And we can see how where's the, what do we got, an equinox there, a solstice down here, another solstice over here, and those are just the main hour angles around the sky. There are 24 altogether. I don't know if I mentioned it or not, but 24 and 0 are the same thing, right? When you get back to the starting point, the 24th hour is the same as 0. Okay, here's the picture which shows the ecliptic, the plane of the Earth's orbit, as being horizontal or flat. And the tilt that we see, here's the tilt of the Earth's axis, 23.5 degrees right there, which makes the celestial equator, this dark line, tilted 23.5 degrees. Now, the way solid geometry works is in spherical coordinates is kind of neat. We've got an angle right in here that's 23.5 degrees, right there and there. But on the surface of the sphere, it's 23.5 degrees separation here and there. So it turns up in 2 places, at the intersection and at the widest separation points. Those are all 23.5 degrees. Does anybody have any question about this slide, because it shows the relationship between the plane of the Earth's orbit and the plane of the Earth's equator and how they interact with each other? Any question about that? Did you get it? Yeah. Okay. Measured eastwardly along the equator, starting at the vernal equinox. 24, same as 0. Okay, the hours of right ascension are also subdivided into minutes and seconds. But here's where, if you're interested in this, stay tuned. Otherwise, if your concentration lapses for a few seconds here, that's perfectly all right. But because we are going into the difference between the minutes and seconds of right ascension and the minutes and seconds of declination, they're not the same. Because they're 360 degrees of declination and 24 hours of right ascension. So when we start dividing those up by 60, we're not going to get the same thing. They'll be different by a factor of 15. 24 into 360 is 15. So 15 degrees of declination is the same as 1 hour of right ascension. So if you figure out what 1 hour of right ascension looks like in the sky, it's the same as 15 degrees of declination this way. Now, that seems reasonable until you get down to where we're comparing minutes. Here's 15 minutes of declination. We've just divided that by 60, right? We've divided this by 60 and taken an hour into a minute, and that's a minute of right ascension. No problem there, except when you go back and forth. 15 minutes of declination is 1 minute of right ascension. So I'm mainly bringing this up to avoid confusion when you run across those later on and something is like 15 minutes east of another object. Well, that's along the right ascension line. 15 minutes north or south is a whole different ball game because we're talking about declination then. So when you're finding things, if you don't have an automatic telescope that finds everything for you, you have to remember this, that there's a factor of 15 difference. And same with the seconds. Here we go. You've heard of sidereal time, probably, and maybe wondered what it was. The Latin words, there are actually 3 different words in Latin for star. The one you're most familiar with is probably stella. But sidus is another one, genitive sideris, from which we get the word sidereal, which means pertaining to the stars. And the Earth rotates on its axis. We've been saying 24 hours, but with respect to the stars, it's really 23 hours and 56 minutes. So if a particular star, say, crosses the meridian at a particular time on one night, the next night it will cross, I said 4 minutes earlier, that's 23 hours, 56 minutes later. So the Earth makes one rotation with respect to the stars every 23 hours, 56 minutes. And that is a sidereal day, one rotation of the Earth with respect to the stars. However, the Earth's revolution around the sun carries it a little farther around its orbit every day, about a degree. Consequently, the Earth has to turn a little bit farther to aim back at the sun again. It's at the same place it did on the previous day. So that takes 4 more minutes for the Earth to rotate to catch up to where the sun has moved in the sky over that 1 day period. So the solar day, we define that as being exactly 24 hours long, but the sidereal day is 23:56. And this is where, while we have that thing about the sun, or the stars rise 4 minutes earlier every night. Okay, here's a diagram that shows that. Okay, here's the Earth rotating on its axis, and in 1 day it will make one complete revolution with respect to the stars. This arrow happens to be pointing towards the sun. This one is also pointing in the exact same direction, but you can see over here it's not pointing towards the sun anymore. It's noon at this point on the Earth, since that point is facing directly towards the sun. 23 hours and 56 minutes later, the Earth is at this position again. However, it's not aimed at the sun again. It's not noon there. We have to wait another 4 minutes for the Earth to turn a little farther to be aimed at the sun because of that motion around the sun. So that's the difference between the 23:56 and the 24, between the sidereal and the solar day. Okay, the clocks run on solar time. What if we went by sidereal time? That would be kind of a mess, wouldn't it? Because 12 noon would be midnight 6 months from now, you know. So it would be, you have to have some kind of a standardization where the sun crosses the meridian at about noon every day, by the solar time, except for when we have daylight saving time, which throws it off an hour. And then sometimes it's ahead or behind a little bit, which is another topic. But we have to use solar time to live by. But the sidereal time is what the sky goes by, the stars at night. So sidereal time is the same as the hour of right ascension on the meridian. So you can see what the sidereal time is at any time by setting your planisphere to correspond to the sky, and then just read off the hour angle, and that would be the sidereal time if you need to know it. And as I said before, that's a 4-minute difference every day, but over a year's time that adds up to another whole day. So there are 366 and a quarter sidereal days in the year. The Earth turns around 366 and a fourth times with respect to the stars, but since it's gone around the sun once, you save a day that way. So it only takes 365 and a fourth solar days to make up a year. So we're off by a whole day over a period of a year. Okay, you can set a clock. This used to be done a long time ago before you had all kinds of electronic things. You could tinker with a clock and make it run 4 minutes fast a day and keep sidereal time that way. Or set the drive of your telescope to track the stars by using a regular clock and adjusting the speed to where it was keeping sidereal time rather than solar time. Okay, back to the seasons and tilt again. 23.5 degrees, we've seen that. The northern hemisphere, the Earth tilts towards the sun in the summer. Okay, suppose the sun is here, here's the Earth with its tilt. In the summer, the northern part where we live is facing the sun. In the autumn, or excuse me, in the winter, we're around on the opposite side. Our side of the Earth, the north end, is tilted away from the sun. So we get shorter days, longer days over here, and the angle, as you know, outside in the sun in the summer, it seems to be bearing almost straight down on you, where in the winter, the sun comes in at a low glancing angle, and 1 square foot of sunlight can get spread out over 3 feet on the ground, and its effect is diluted that way, so it has less of a warming effect. So those two things, the length of the day and the angle that the sunlight comes in, are the causes of the seasons. At the equinoxes, sun is up 12, down 12. Summer, sun's north of the celestial equator, it's up more than down. The winter, it's down more than up. And that, what I was just talking about, the angle that the sunlight comes in, that's insolation, not to be confused with insolation, like electrical or thermal insulation, but insolation is the incoming energy from the sun. That's seasonal temperature changes due to that. Here's a picture of that. We've got the Earth going around the sun during the year. Here's the summer solstice, where our tilt is aiming us towards the sun. In the winter, our side is facing away from the sun, and the angle of the sunlight coming in is lower. At the spring and fall, we're kind of at right angles to that, and we get equal days, equal nights. The tilt doesn't make any difference because it's neither towards or away from the sun, but sort of parallel with it. Okay, any question about that one? That's the seasons. Okay, Arctic Circle. Here's an interesting place on the Earth. It's located 23.5 degrees from the North Pole, or at 66.5, which we've already seen was that place in Sweden that we went to a little earlier on the latitude trips. Within that Arctic Circle, the sun gets actually to be circumpolar. It's so far north, and Polaris is up so far in the sky that the sun doesn't ever get a chance to go below the horizon. It becomes one of the circumpolar stars then. And so it's out constantly. And the land of the midnight sun, I'm sure you've heard of some of the Scandinavian countries referred to as that, because even at midnight, the sun is just glancing along the northern horizon at the Arctic Circle. If you're farther north, it'd be up, more than that. And near the winter solstice, the sun is below the horizon day and night. If you're at the North Pole, from the end of September till the end of March, the sun is not up. Next time you watch Polar Express or some such movie as that. See how many mistakes they make regarding the astronomical events in there, including being able to have daylight at all at the North Pole on Christmas. That's when it's farthest below the horizon all the time. Okay, already just covered that, and we've already seen that. At the North Pole, the sun only rises and sets because of its motion along the ecliptic, not because of the rotation of the Earth. That's just the merry-go-round going around parallel with the horizon. Okay, let's look at that on the software. Got ecliptic and celestial equator. Okay, we have to rotate that and bring up. Well, here's our present situation. Here's where the sun is in Pisces, north of the celestial equator, so we're heading towards summer through the spring. Here we go through Gemini. There's Taurus. There's Venus right there. There is the summer solstice right there, right by M35 in Gemini. It's where the sun is as far north from the celestial equator as it ever gets. Okay, move this up until we get the present evening sky with Leo coming up. Coma Berenices should be right about there. And the autumnal equinox in Virgo. Bring it up far enough to see Virgo and Spica. There's where the sun will be coming back down in the first day of fall, crossing the celestial equator, heading towards the south. We turn towards the east, southeast. Bring it up a little farther. We get to the winter solstice. Here's the sun getting farther and farther south. There's Scorpius. And into Sagittarius, just coming up. It's over here, and here's the 0 hour angle. I don't think you can see that 0, but there's where the 0 is right there. That's where the farthest south the sun gets in the sky. It's when it's just coming into Sagittarius on the first day of winter solstice, 18-hour angle. Okay, back to the vernal equinox. And we want to face south while we're doing that. Here comes the vernal equinox, the first day of spring. And moving around towards the south. And there we have it. Here's where the celestial equator is. Here's the ecliptic. Here's the sun's path through the year. You can see how drastically the sun changes its height in the southern sky at noon during the year. Let's back out just a little bit and see, we're in the summer in Gemini. Let's move this down just a little where you can see the zenith. Sometimes seems here like the sun is straight overhead in the summer, doesn't it? There's shadows very short, first day of summer. Well, it's not exactly straight overhead. It's here and there straight overhead, but only a few degrees difference. If we were farther south and the zenith would match up with this, exactly, that would be the Tropic of Cancer, the 23.5 degrees north of the equator is where you would be, and the sun would be straight overhead. Anywhere between the two tropics, the sun is overhead at some point during the year. Okay, now let's go back to Fairbanks, Alaska, and see how it looks, how the seasons look different from there. Okay. Fairbanks, Alaska. Okay. Eliminate the plane trip. I want to face south and let her roll. Okay. You can see that the sun can be nearly just below the horizon there, facing south. It doesn't ever come up above it just grazes along the horizon. Let's speed things up here and go to Kiruna, Sweden again, where we can actually see the midnight sun. I think it took it. Yeah, it's got the right. Oh, okay. Here's the ecliptic. There it is during the winter up there, way below the horizon. And we will see that when we get the summer constellations like Gemini coming along, and the ecliptic is back up again, that when we're looking at the northern horizon, the sun will just be going right along it. It's coming. Here we go. All right, there it is in Pisces, getting farther and farther north. As we're going into the summer, it's Taurus. And here is the first day of summer with the summer solstice right there. Watch what happens on the first day of summer at Kiruna, Sweden. This moves along, and just about this parallel or tangent, other than that little mountain peak right there, the sun is going grazing right along the northern horizon and never really sets on the first day of summer. And of course, if you were farther north, it'd be up even higher. Okay, now the very last topic for this evening is precession. And to me, that's one of the most interesting things that happens, is the whole concept of precession. Remember we said the Earth's axis is tilted 23.5 degrees, but that direction of the tilt isn't constant. During our lifetimes it is, but it actually wobbles around. Hipparchus discovered this more than 2,000 years ago when he was making sky maps, kind of like I was, and discovered the rotation of the Earth. He discovered precession, that when he would come back years later and plot the exact positions of stars on his sky map, they had all moved systematically, that his coordinate system wasn't holding. And that's because the Earth's axis was wobbling. So Bill will cover this next month on the phases of the moon and tides and eclipses, is the gravitational pull of the moon on the Earth's equatorial bulge is what makes the axis of the Earth wobble around. It's kind of like a gyroscope that's slowing down and wobbling around as gravity tries to pull it down. It makes it precess. So the celestial pole traces out a circle, 23.5 degrees in radius, centered on what we call the north ecliptic pole in Draco. That would be, if you, again, go back to the solar system as a flat plane and went straight up from that, there will be a spot in the constellation Draco where that's the center of the precession circle. All the north stars are in a circle around that, 23.5 degrees in diameter. So that's the axis of the solar system, points to that north ecliptic pole in Draco. So there's actually a succession of north stars. Polaris hasn't always been our north star. When the pyramids were built, the star Thuban, Alpha Draconis, was the pole star. And then after Polaris, the stars along the east edge of Cepheus. You look at your sky map, you'll see that the stars on the edge of Cepheus will become successively the pole stars. 12,000 AD, Vega will be the north star. Now that'll be something, a bright first magnitude, actually 0th magnitude star being the pole star. That would be really handy. What's that?
Boy Scouts will start getting it right then.
Yeah. Most people now, most people think the North Star is the brightest star in the sky. And it's actually about 26 or something like that, but it'll be one of the handful of brightest by then. So that's something to look forward to, 12,000 AD. Okay, here's the precession circle. Here's the middle of Draco. There's the north ecliptic pole. That's where the axis of the whole solar system points. Right now, the axis of the Earth points over here at Polaris, 23.5. That's your tilt right there. Here are the stars along the edge of Cepheus that will be the subsequent North Stars. It'll eventually get close to Deneb, and then around to Vega, and then back to Thuban again, the one that was there in the time of the pyramids. Now, not only does the pole wobble around, but the equator wobbles around too. It has to. It's attached. It's 90 degrees apart. So the equator wobbles just as well. And that intersection point between the equator and the ecliptic, the equinoxes, that moves around the sky as well. So the vernal equinox gradually moves through the constellations westward due to precession. And since it's such a long time period, it spends about 2,200 years in each one of the constellations along the zodiac. So it takes a long time to go all the way around. 2,000 years ago, the vernal equinox was in Aries. In fact, you'll still find some astronomy books that call the vernal equinox the first point of Aries. If you don't like right ascension, you're not going to like the first point of Aries either. But that's what it's still referred to, even though it's now in Pisces. We refer to the Pisces era as the Christian era. And then, eventually, the vernal equinox will move farther westward into Aquarius, which is what is meant by the term the dawning of the age of Aquarius. Remember the Fifth Dimension song about that? This is the dawning of the age of Aquarius. What that really means is that due to the moon pulling on the Earth's equatorial bulls, the tilt of the Earth's axis swings around in a circle, and the point where the celestial equator and the ecliptic intersect will gradually move westward from the constellation Pisces into Aquarius. But that's an awful lot of words, so they just said, this is the dawning of the age of Aquarius. But that's what it means. So, but also, precession slowly changes the right ascension and declination of every star, since they're measured from the celestial equator system and it's wobbling around. This is what Hipparchus discovered when he was making his catalog of all the known stars and their positions. He discovered precession and even guessed within a couple of thousand years of how long that cycle would take. So he had a marvelous scientific career more than 2,000 years ago. Okay, here's the precession of the equinoxes. People have heard of that term, but most people have no idea what that means. Here's the precession circle we were just looking at. And there is Thuban there's Polaris, and there's the Cepheus stars, and Deneb, and Vega. That's the precession circle. But this shows the celestial equator moving as well. First of all, here's the ecliptic. The ecliptic is eternal and unchanging. The orbit of the Earth isn't changing unless some giant planet comes by and tilts everything differently. So the ecliptic is always going through these constellations, but the equator changes as the Earth wobbles. So here's, well, the color code comes up here. Yeah, the present, the green one, here's the celestial equator that's on your map. The present situation intersects in Pisces. Okay, the vernal equinox in Pisces. Here was when Thuban was the North Star here. Here's where they intersected then. And you can see that that is in Aries, the first point of Aries. And eventually, when Vega becomes the North Star, the celestial equator will have moved down into Capricornus, believe it or not, and the vernal equinox will be right there. So that's how the equinoxes precess westward along through the constellations of the zodiac. Now here's where the astrologers have messed up. They base your whole life story on what sign you are. Well, that was all set up when the equinox was here in Aries. Now it's another constellation over, going on, actually it's getting pretty close to the next one. So if it ever did mean anything, it doesn't mean the same thing anymore. because all of the constellations are off by more than one from when all of those things about your personality and everything were set up. So astrology is based on outdated, well, that's another whole topic. But at the very least, it's outdated by the precession of the equinoxes.
22,000 years will be ready again.
Could be, yes. Now, this will finish everything up for tonight. The last grand finale here with the, let's see, where are we? Precession. Oh, I want to get rid of that, yes. I want to get this back. Okay. I need to get a couple of more coordinate systems up here. So view, we've got to get the ecliptic guide and go with the ecliptic and but not the grid. And the options, we want the ecliptic meridian, ecliptic poles. Yes, we've got to have that. All right. And then under options, we want to go back to Memphis again. And we're facing north. Okay, so this is back to the present time, except we see the north ecliptic pole in Draco moving around. No particular significance right now until we do this. Okay, we're at 1,000. Okay, we want to put Thuban at the top. So it's getting ready to come on around. There is Thuban right there, the former North Star when the pyramids were built. It was said that they built it so that the light from Thuban would come through a little hole in the pyramid and shine down on one of the ceremonial altars or something inside. I'm not an archaeologist, but I've heard that from people who claim to know that they had that set up where they could get the light from that star to come through. Okay, I'm going to stop it right here. And I'm going to set the date to 2700 BC. So 2700 and BC. And now we move again, and guess what? The North Celestial Pole is on Thuban. The whole sky is turning around Thuban. And here is Polaris over here, obviously not the pole star. You know that they didn't call it Polaris back then for obvious reasons. They had another name for it. It was Al-Ruccabah, A-L-R-U-C-C-A-B-A-H. So that was the name of Polaris before it was the pole star. Kind of reminds me of Rebecca's email address for some reason. Al-Ruccabah. Okay, now let's put it into the Christian Empire in period. So 6 BC. Our best estimates of the birth of Christ. We can see that the North Celestial Pole is now somewhere between Thuban and Polaris. It's in that area. We go to 4000 AD. Let's do that. Moving ahead. 4000. Come on here. 4000. Okay, now what? We can see it's right near Gamma Cephei right here is the North Star then. Not much of a North Star, but it's better than anything they've got in the southern hemisphere. Now let's go up to 10,000 AD. Now the North Celestial Pole is fairly near Deneb. It's not right on it, but you've got a pretty good idea which way is north. And of course, all of these stars are circumpolar now, including all of Cygnus. And finally, 13.5. And we can see that Vega is very close to the North Celestial Pole. And the whole sky is circling around Vega. Now, I got a preview of this a few years ago, if you don't mind a personal story. And it wasn't when I was the planetarium director and could do all of this indoors. This was outside. I was out in a fishing boat in Pickwick Lake, and we were anchored, and it was late at night, and I was lying back with my head on a pillow on the seat of the boat, And there was enough breeze there to just kind of blow the boat back and forth. And Vega was almost straight overhead. And the whole sky seemed to be rotating back and forth around Vega. So I got a preview of what it would look like in 13,500 with the sky circling around Vega. Now let's look in the southern sky here and see how different things look. Recognize stuff? Here's Pisces. Here's Auriga going by in the southern sky. Here's Orion just barely clearing the southern horizon. This is Memphis. We're at Memphis. We don't see Sirius here anymore. It becomes like the Southern Cross. You have to go south to see it. So and notice something else. Notice Gemini's shape has changed. And Bootes, here, golly, look at that. Let's pull that down a little bit. That doesn't look like Bootes anymore, does it? Is that a flaw in the software? No. They've counted the proper motions of stars, and over the 10,000 something years between now and then, they've actually moved around quite a bit. So the constellations have changed their shape. So, and let's see, the last thing I want to show you. The celestial equator, that's different. The ecliptic's still right where it was, but the celestial equator crosses in Pisces, doesn't it? However, look at this. This is where the sun would be going southward. This is now the autumnal equinox. Now that we're on the opposite side of the ecliptic circle, the equinoxes and solstices have reversed. And here is the winter solstice down in Gemini, where the sun is as far south as it gets. So you'll have to learn everything all over again when we get to 13,500. Okay, just back to this for long enough to wind up. And there you have it. Wow. Okay. I'm applauding you because that was as much work for you as it was for me. And next month, Bill will be talking about the sun, earth, and moon, and the phases of the moon, tides, eclipses. Then we get into the early history of astronomy, the formation of the solar system, stellar evolution, all kinds of wonderful, interesting, beautiful things. So stick with us and you'll come out ahead. Don't forget observing Village Creek if you haven't signed up. Anything else, Mark? We'll let you know by email. So, okay, thanks for coming. We'll see you next time.
Thank you.
Yeah.